I wasn't sure what the audience would be, so it will be a little bit more introductory in the beginning. So in particular, when I talk about mathematical structures, I was thinking what exactly to talk about, because there's been so much progress in the last decade or so. So I'll focus on one aspect of interesting mathematics that we see in scattering amplitudes, which is that of cluster algebra. So even though the title is mathematical structures, so more technical description would be the cluster algebra structures in scattering amplitudes. Okay, so here's the outline of my talk. So I'm going to start with the introduction to amplitude. So there's a lot of people working in this field, and this field evolved in the last 20 years. So I'll kind of like review some of the motivations, why we're interested in this, and what the big goals are. Then I will tell you a little bit about the status of some of the computations and the methods. In particular, there are various theories that one can look at, various quantum field theories. So the two examples that I will be focusing on is, one is n equals to 4 super Young-Mills theory, and also massless QCD. So we've been very excited recently because some of the results that's been up there for over a decade for n equals 4 Young-Mills theory now could be generalized to massless scattering. So I will tell you what the status of those computations are. So that would be kind of the physics part. And then I'll talk about the mathematics. And given the data that comes from physics, given those quantum field theory objects, I'll tell you about the structures that we observe, and in particular cluster algebra structures in these in this object. And then I'll end with an outlook and interesting questions that a lot of us are thinking about. All right, so I'm going to start with the motivation. So a typical LHC collision looks like a mess of particles, which looks like that. And there are lots and lots of ingredients that enter in these calculations. So the focus of my talk today will be the building blocks of any LHC collision, and the skeletons of any quantum field theory process, namely scattering amplitude. So I'm not talking about the rest. I'm just talking about the scattering amplitudes. So of course, the standard model has been tested to a very high precision at the LHC. However, if you look at the standard model total production cross-section, and if you look at the ratio of data to theory, so the main thing you need to take out from this slide is this ratio. And if you see that the gray, which is theory, the arrow bars start being, so once you move from 2-body final states to 3-body final states, the arrow right here, so the arrow bar starts being larger, and that's because it's still very challenging to compute next to leading order effects at 5 particles. So that's the 3. So these are the 3-body final states. So that's you need for this the 5-point scattering amplitudes at next to leading order. So another slide. So this is again just to continue the motivation. So of course the advancement of our understanding of physics at high energies relies on a detail, as you've seen in the previous slide, relies on detailed comparison between experimental measurements and theoretical predictions. And every couple years there is a meeting in Lizouche where there's a wish list being made. So this is I think the latest, which I took from the last from a presenter at the last Amplitude conference, and you see, if you go back 2 years, you see that there are various processes that are known, and there are also a lot of processes that are being desired to be known. So again, that's just more of a motivation. So everyone agrees that these are important objects and they have to be computed to high precision. Now, what are those Amplitude folks doing? What are the goals of the program? Well, the program is a twofold. On one hand, one would like to explore the rich mathematical structures that we see in scattering amplitudes in any quantum field theory, but we don't want to just study abstract mathematics, and in particular, we don't want to study abstract mathematics and some obscure theories. We'd like to exploit these structures, and we would like to apply any tools that we develop to realistic theories, and we'd like to be able to compute something new. So anytime somebody comes up with a new methods or new techniques, new structures, new mathematics, one really wants to ask a question: are you able to compute new things that nobody could compute before with these new tools? And I like to also, this picture, which comes from Zvi Bern, and it shows you that the success of this program rests on two pillars. On one hand, I'm just repeating again, we are exploring the structure, symmetry, beauty, anything of these objects, such as scattering amplitudes. But on the other hand, we would like, we need always to have a second pillar. We'd like to be able to produce results that are useful outside our field. So to thrive, we really need support of both pillars. Okay? So that's the goals. Now, okay, so what's this scattering amplitudes program is all about? So like I just emphasized that the program started in collider physics, so the motivation comes from the LHC and from comparing to, theory to experiment. But in the last decade or so, 2 decades or so, the amplitudes programs blossomed into various directions. So I think it started somewhere here, but now people are computing also these amplitudes with huge success, and in classical gravity, and applying these to gravitational waves. They're very impressive computations. There are also interesting results in QCD. This led to some of the new formulations of fundamental physics. And of course, some aspects are also very formal. The N=4 Young-Mills theory, which is one theory that I will be talking about, string theory, integrability, and there are also very deep connections to mathematics, and now there are a lot of mathematicians joining these fields, so connections to algebraic geometry, number theory, etc. Okay, so this is also visible in the list of the snow mass topics. So in the US, there is a snow mass process every 5 years, and there's a report which now is a couple years old, and there's a section devoted to scattering amplitudes, which was put together by Zvi Bern and Yaroslavchenko. And if you look at the titles of that section, you see a lot of different topics, just like I had on the previous slide. So, for example, computation challenges of multi-loop collider phenomenology. There are more mathematics for precision collider physics. This is our N=4 little white paper. There are gravitational waves and scattering amplitudes. There are certain moral effective field theory. There's string perturbation theory. And finally, there's also applications to cosmology. So what I'm just trying to emphasize over and over again, that this is a broad program which grew in the past several years, and now it covers a lot of so it starts with these fundamental objects, scattering amplitudes, but one can go into various directions and compute them in different theories. So this field started, it's been already almost over 15 years. It started at a small enthusiasts. The first Amplitudes conference was in 2009 in Durham. There were only 56 of us. And then it started growing. More people joined the field from all sorts of subfields of theoretical physics, from mathematics, from formal. My background is in string theory, from collider physics. And for example, I think the records, but this is kind of cheating because that involves the online participants, but there are over 400 participants that went, but I think there were, consistently there are over 200 participants, but if you include the online, there were 400 at CERN. So this year we just had the conference 2 weeks ago in Seoul, and it goes on. So this is a 20-year span already of the Amplitudes program. So it's became a field on its own. Very good. So that's kind of the introduction to this field of computing scattering amplitude. So let me just be a little bit more precise and tell you a little bit about status and methods of some of this computation. Again, this is a huge program, and I don't have time to cover everything, so I thought I'd just focus on particular two theories. So I'm going to start with okay, so scattering amplitude. So before I get a little bit more technical, so the amplitudes are characterized by by 3 integers. There's n, k, and l. So n is the number of particles. So you can have, so this terminology will be used over and over again. So you can have 4 point, 5 point, 6 points. So you have 2 particles come in and 2 particles come out. That's the 4-point amplitude. Then you can, so most of the amplitudes I'll talk about are going to be gluon amplitudes, but you can talk about helicity sectors. So the language will be used are MHV and MHV. That's how many positive or negative helicity gluons you have. So K, so for example, MHV has 2 negative helicity gluons, all positive, and MHV has 3 negative helicity gluons, and then the rest is positive, etc. So that's a helicity sector, and the language will be, MHV and MHV and squared MHV, etc. And then there's a loop order. So you can have tree level, just when the diagram looks like a tree, then you have 1 loop, 2 loop, 3 loops, etc. So N, K, and L are the numbers that you need to remember. And in principle, we know how to do them. It's quantum field theory 101. You draw your something called Feynman diagram with N external edges and L internal loops, and then you have to do the integral. Okay, so what is the status of these computations? So let me just right away focus on just massless integrals. And interesting enough, it's not that much. So up to 2 loops, only recently the 6-point. So again, you can have 4-point integrals, 5, 6, etc. Only recently, in these 2 papers by Abrumani, Page, and Volovich, and Hen at collaborators, only recently the massless and planar 6.2 loop amplitudes have been exactly evaluated. And these are the integrals that I've drawn. So despite years and years of studying. So again, I just want to say right away, in this talk, everything, when I talk about amplitudes, is going to be I refer to the final expression to after you do the integral, because some of people might have heard like amplituhedron, polytopes, that refers to the integrand. So just some people get confused. So here, everything will be final integral. You have an integral, you're interested in the final expression. So, okay, so what we need to remember is for massless integrals, only recently have been evaluated up to 6 points, 2 loops. Now, the status so why are we interested in more exotic theories such as n equals 4 Yang-Mills theory? Well, because much more is known. And so if you so this is a chart of the status. So if you start with, first of all, tree-level amplitudes are known for all n. Now, the 4 and 5-point amplitudes are also known to all loops. There's something called Baer-Dixon-Smirnov ansatz for that, which is known for over 20 years ago. Now, if you go to 6 and 7, recently, it's only recently that, so the current status is the 6-point amplitudes have been computed to 8-loop order. And by that, I actually mean the actual final answer for the integral. And that's been developed for the past decade by Lance Dixon and collaborators. So that's, I invite you to see the review. But the 8-point computations are in this paper by Dixon and his former student. When you go to 7 points, everything is known up to 4 loops. Okay, so that's quite impressive, and it's probably currently the state of the art. and nobody would disagree that 8 loops is really, really impressive. So there are also a couple other amplitudes unknown due to the work actually of Song Ki and his former students here in Beijing. So there are 8 and 9 point amplitudes unknown to 3 loop and 2 loops that I will say a few words about momentarily. Okay, so you see the radical change from 6.2 loops to the 6.8 loops on the slide. So why is that? Well, this is a very special theory. The theory called N equals 4 Yang-Mills theory, and some of us studied it for the past decade. And why are we doing this? Well, because it has additional structures, such as the amplituhedron that probably some of you heard, many of you heard about. It has dual conformal symmetry, it has Youngian symmetry, it has cluster algebra structures. So it's a simple model that likely can be solved exactly. But the reason we study, I mean, it's a nice, beautiful theory, but we also study it because we'd like to develop tools and intuition towards our goal of studying more realistic theory. So in then part of the snowmass, we have this so this is already 3 years old, kind of to that moment summary of the situation in that theory. Okay, so let me just say, okay, so this was very general, so I'll start getting a little more and more technical. Okay, so let me focus for now on N equals 4 and then go back to massless scattering. And so these scattering amplitudes, again, we can think of them, we're going to be thinking of them as some functions that arise. So these are functions of certain kinematics that arise after you do the integral. So how does that go? So first, there are 2 things I need to tell you. So number 1 is, what are these amplitudes functions of? So, you know, you have f of x. What is x? What's the space of kinematic? Okay, so normally when we compute amplitudes, we talk about momentum and polarization. We write as scattering amplitudes as a function of momentum and polarization. So for this special theory, N equals 4 Yang-Mills theory, we, instead of labeling the amplitudes in terms of the momenta, we label, so, and there are n of them for n particles, we label them in terms of the n vectors in P3 that actually, more mathematically speaking, they lie in a Grassmannian of 4 planes in n dimensions. So these z's everywhere, instead of p, there will be any point p corresponds to the line of z's. So everywhere, when I draw something, there will be, so instead of writing f of p, I'm writing f of z's. And moreover, once you have these z's, which lie in 3-dimensional projective space, I can form, so these z's are has 4 components. I can take 4 of them and I make a 4x4 determinant. And that's what these are called Fluker coordinates on CP3. So everywhere you'll see those brackets. And there's a map, which I'm not going to go into, but just pictorially. So everything, these are also sometimes called momentum twisters. So these are the coordinates that will be appearing. Now, this is the kinematic, so f of x, what is f, what kind of function? So the reason this theory is simpler is that the theory has something called uniform transcendentality, the N equals 4 theory. So if you look at the L loop amplitudes, it turns out it has, the final expression has transcendentality 2L. So what is transcendentality? So for example, pi is transcendentality 1, pi squared transcendentality 2, log is transcendentality 1, log squared 2, etc. So if you go to more complicated functions than log, you have polylogs. They are defined by the recursions like that. So the Li1 is just a log. So that this polylog is transcendentality M. So at L loops, for example, at 2 loops, they are going to be transcendentality 4. So we Li4, Li2 times Li2, etc. So then, so these are ordinary polylogs. Then one can talk about generalized polylogs. And these are the functions which, if you look at the definition of the polylogs, you see they're given by the iterations like that. So, you know, if I didn't have m equals 1, this would be dt by t, that's log. but then you recurse them like that. However, if you sprinkle, so this is a t denominator. However, if you put some arbitrary parameters a in the denominator, you get something called generalized polylogs or multipolylogs. Sometimes they also call Goncharov polylogs. So that's the types of functions that appear in this theory up to 10.2 loops n cubed MHV. Starting at 10.2 loop n cubed MHV, more complicated polylogs, and these are called elliptic polylogs, start appearing. And we also have a nice, with a collection of co-authors, we have a nice review on those functions in actually probably my only paper in PH, which I'm super proud of. So, explaining what these are, and there are a lot of people who study these this function, and this kind of on its own right, it's on its own, yeah. So it's on its own became kind of a subfield. Oops. This became a subfield of amplitudes. For example, they have their own, like for the past 10 years, they have their own elliptic meeting. So, but these are just a mathematical physics problem to study those functions, study their observed properties, and they even got the RC synergy, like Volovich and others have been developing this. So they even received the RC synergy grant to devoted purely to studying these polylogs. But it's an important, it's very important problem in mathematical physics, which has a lot of applications, just because these are the polylogs which appear in a study of these amplitudes. So how do you normally, what do you do? How do you deal with these polylogs? Of various codes that people write. Claude Dour, for example, is one of the authors of polylog tools. There's other codes, but an important object that plays a role everywhere is called symbol. So, and let me just tell you what that is. So, anytime you deal with multi-polylog, elliptic polylog function, so this is just for polylogs, not for elliptics, but such function, as you saw in the previous slide, could be written defined recursively like this. So you can also rewrite it, get rid of the integral, just write df is f d log x. And the symbol of that function is defined basically by recursively looking at the arguments of this log and then recursing it through this. So for example, this symbol of log x is x, symbol of Li2x is defined by -1 minus x times x. So for transcendentality m function, you have a m tensor product. And anytime you deal with these functions, you have this collection of arguments that appear in the symbol, and these are called letters. And together they form a symbol alphabet. And the reason it's important is because it makes the identities between various polylog functions very easy. So for example, if you have an identity of this sort, that's a very well, you can prove it, of course, by doing integrals. But with a symbol, with the definition that I showed you on the previous slide, it's very, very easy to see why this identity is true. You just take symbol on both sides, symbol of each Li2 is, I showed you in the previous slide, and then you put this together, and this is 1 minus x squared tensor x, and that's nothing but the symbol of Li2 of x squared. Now, that's mathematical. So practice, anytime you need, you're doing integrals, it's became a standard tool. And this alphabet also, the physics of this alphabet and these letters is that it encodes all singularities of a function. And it's been 15 years since this technology was introduced, and we're actually organizing to highlight this developments, because it's been had a lot of applications in QCD integrals. We're having the meeting in December. Okay, so now let me give you some examples of how these amplitudes actually look like, because I've been very, very vague so far. So let me write even more formulas. So as I said, the first non-trivial example, if you go back to the slide, the first with the status, the first non-trivial example so everything of 4 and 5 points have been known. But the first non-trivial example where you get some non-trivial function starts at 6 points. And if you look at the two-loop function, it's been known again over 15 years. And as I told you, for two loops, we have transcendentality 4, so it's in E4. And the arguments are various brackets of Pluko coordinates that I defined. So that's how the two-loop 6-point MHV amplitude looks like in N equals 4 Yang-Mills theory. Now, if you ask how does the alphabet look like for that function, it looks like this. So I also wrote here, just for the future, I need only also 6 and 7. So these are the letters. The letters are just these brackets everywhere. So for 6 points, you get just these various brackets, 1, 2, 3, 4, etc. And there are 15 of them. Starting at 7 points, you can have the quadratic expressions in these brackets, and there are 49 of these cyclics. So they start looking like that. So here I've just written what is this, and that's a focus of some of the rest of the talk. So what is the simple alphabet for these amplitudes? So what is the set of arguments that these functions depend on? Okay, so that's the way it looks like for 6 and 7. Now, starting with just this example, starting with two loops, 6 and 7, it turns out that one can use a bootstrap, which is the following. You start with a simple alphabet presented on the previous slide, and you can bootstrap to high loop up to 8 for 6 points, by basically saying the following: okay, my symbol has only these entries. Now let me impose various physical and mathematical conditions on this symbol. And here's, for example, some slides. It goes up to 6. So this I took from this review. So you start, and this is for MHV and for NMHV 6 points. You start with this many entries, and then you start applying various, these alphabets have to behave. The symbol has to behave in a proper way under collinear limit in multi-radial kinematics, etc. But remarkably, by starting with this ansatz, with big ansatz, and solving essentially a large system of linear equations, Dixon and collaborators were able to find a unique solution, which is very remarkable because there's no guarantee that it existed. So these 6 and 7 point amplitudes have been computed to 8 loops. Now, what about higher points? So the higher points have been investigated by Song-Hee and others. And there are two. I have some slides with some simple alphabet at 3 loop 8 points, just to show that these folks did the work. But the main thing you need to remember is that that some of the alphabets start involving. So I said previously everything was these brackets, so quadratic and brackets, but everything start involving square roots. So again, the alphabet has been worked out. Okay, so recently, so this has been going on for some time, but recently there's been progress, and so over the years, some of these results have been generalized to massless scattering, and in these papers by Hen and others, a lot of integrals have been computed. So if you look at 2 loop 5 point massless integrals that are drawn here. So the symbol alphabet for planar and non-planar has been worked out in this series, and it looks like this. So S12 is P1 plus P2 squared. I don't want to go into great detail, just to tell you that the alphabet is known, and yeah. So maybe I skip this, and then so very recently. So this is from this year. The 2 loop 6 point integrals have been evaluated in these papers. And just so, again, to show you that the work has been done here. So for example, the full alphabet is for full alphabet for planar 2 loop 6 point amplitudes is given by 245 independent letters. And the letters look something like this. So let me just, so you have 9 V's, which are some Mandelstam invariants. And then it gets more and more complicated. So there, the V1 is something like these are numbered through 275, but there are various permutations. But I schematically, of course, if you open the paper, it's several pages just to present it. But I thought it's useful to just put it on the slide. So first, there are 48 letters that are linear in V, then there are letters that are quadratic in V, then the letters cubic in V, then there's square roots, and there are more square roots, and there are more complicated ratios that start appearing. Okay, so the reason we start getting excited is because more and more data on the massless integrals has been obtained in these papers recently. So now, okay, so there's a data. So I've told you physics data for n equals 4 and for massless scattering for these final expressions for the integrals. So what about math? So again, I'm not the one doing the hardcore calculations. Somebody is doing hardcore calculations, large groups, lots of young folks. So, but we would like to be just kind of like engineers. We'd like to take the answer and see if we can see the structure. Because why is it interesting? Because if we see the structure, then maybe we can do another example. So what we would like to ask so take the list of simple alphabets for n equals 4 and for the integrals, and we would like to ask, is there a mathematical description of this symbol alphabet? Okay, and there's been, for n equals 4, there's been some progress over the years. So I will focus on just relation to cluster algebras, including the definition of what that is, because that recently has been generalized to the massless scattering, but there's various others. There's polytopes, Laplace graphs, tensor diagrams, scattering. There's a lot of mathematics, tropical geometry. So people have been looking at how to get this from mathematics. But let me just start with n equals 4 and then generalize it to massless scattering. So the statement is very simple. The statement is that if you look at the set of letters that I showed you previously here, that I showed you here, so that's again physics result. It turns out that these letters are not arbitrary. They're there's an independent description of those letters, and these are described by Grassmannian cluster algebras. So now what is the cluster algebras? So cluster algebra is the following. Cluster algebra has two things. First of all, it's a huge subject in mathematics. It has its own math subject classification. So it appears in topology, analysis, algebra, number theory, etc. So we're going to be somewhere here. It's radical physics. It also appears in string theory. So we are here bold-faced. So this is from Larry Bolsinger's school at Harvard earlier this month. So it's the subject of cluster algebras is 20 years old. They've been invented by Fomin and Zilivinsky in 2001. And, there are classes, for example. There's a graduate level courses at universities, various universities, describing them. So what is the cluster algebra? So cluster algebra needs two things. It needs initial seed and mutation rule. And then from that, you produce cluster variables. So that those lists of symbol letters would be nothing but cluster variables. So for example, maybe I start with a simple example. So the simplest example of a cluster algebra is something called A2 cluster algebra. It looks like A2 Dynkin diagram. So you have two variables, A1 and A2. So you start like with initial seed, two variables connected with a line. And then you have what's called mutation rule. So it tells you, the mutation rule tells you how do you produce new variables. And it looks very simple. So you start with A1 and A2. Then you look at your quiver, at the graph, dots connected by lines, and you try to produce a third one, and you literally just do, you mutate on A1, and it's 1 over A1, and then you go, okay, number of arrows from 1 to 2, that's 1, and the number of arrows the other way is 0, so that would be A2 plus 1, so that's your variable, and then you continue. So remarkably, this this process for the quiver, which looks like that, the process stops at 5. There are only 5 cluster variables. So that's the best way to learn. There's also cluster algebra portal, but the best way to learn is this book with chapters are available online by Fomin, Lauren Williams, and Zelebinsky, called Introduction to Cluster Algebra. So again, you start with a quiver, you do mutation, and that's your variable. So for example, for the case relevant to amplitudes, we need to talk about Grassmannian cluster algebra, so that we start with a quiver, which looks like that. There's, how flickers, and there are arrows. So that's a very algorithmic way to produce the list. So once you have this, you can give it to an undergraduate student and a student, and you do all the mutations by the formula, very algorithmic, and you get cluster algebra or cluster variables. Okay, so that's a very well-defined object in mathematics. That was A2. So let's go back to what does that have? How is this relevant to the physics problem we started with? So for 6 points, I told you for n points, it's Grassmannian for n. So for 6 points, you start with GR for 6. The quiver looks like that. So you have your, there details, something is box, something is not important. You start with this initial seed, and then you do the mutations according to this formula. So that's very algorithmic. And you get your list. And you get the list of variables, and that's exactly the variables that appeared in the symbol alphabet in the previous, in the physics part. So it's quite useful. Let me just go back. So yeah, so that's exactly these. Okay. So what about 7 points? We want to have these, so the quadratic inflowcurves in brackets. So then you have here. Okay, so you have GR for 7. The initial quiver looks like that. You have another row, basically. For GR for n, you have 3 times n minus 5. So there was 1. Now 2 for 8 is another one. So you start with initial seed like this. You perform mutations, again, very algorithmic ways. And remarkably, you get all these cluster variables, which then match the physics answer. Okay, so we've just learned that 2 loop 6 and 7 point amplitudes are described by GR for 6 and 7 cluster algebras. Okay, however, we want to do more. We're very greedy. We solve one case. We want to do a lot more. So, okay, so what if we go to 8? Well, it turns out that while for 6 and 7, the cluster algebra is finite dimensional, for GR for 8, it becomes infinite. So there's an infinite list. So it looks not very useful and problematic. And moreover, so that's on math side. Moreover, on the physics side, the letters that we see involve square roots, not just polynomials on these in terms of these Pluko coordinates. However, things come to rescue. So for example, it turns out, so still, there is a part of mathematics that helps us. So as I said, for GR for 8, there's infinite number of cluster variables. And it turns out those quivers, for GR for 8, start with the quivers that have 2 double arrows. And it turns out that if you take a simple, so remember the A2 had 1 arrow, but you can take something like, this is called A11. It has 2 arrows, and then you continue this process, and it's infinite. You do back and forth on each node. But it turns out if you take such limit of AI to AI minus 1, the mathematicians have developed techniques to produce square roots. So again, we take some piece of mathematics developed for these particular infinite dimensional cluster algebras, and we can systematically see what is the kind of square root is produced. And indeed, in this paper by James Drummond and others, they were able exactly to produce square roots that appear in scattering amplitudes. Okay, very good. So for n equals 4, we have a good understanding of how the alphabet of letters that appears in scattering amplitudes is related to cluster algebras. And again, why is it important? Because taking that as an input to the bootstrap program that only cluster variables appear, one can bootstrap these amplitudes to 8 loops. Okay, so, but we would like to do more. So we would like to eventually we would like to step back from n equals 4, and we want to study integrals, arbitrary integrals. So there's been two papers, starting with Chechenian and Papathanassiou, and more recently with Papathanassiou and a student, which found the cluster algebra structure in Feynman integrals relevant to massless QCD. So, for example, the symbol alphabet for the 3-loop integral of this form has been worked out in this paper. And it turns out, so there's an answer there. It turns out that, so it's one loop, it's something called A2 that I described to you. Then it's some algebra. At one loop, A2 I already explained. So for for these so you would start with the initial seed of two variables, and so this I already explained. So then these integrals have been computed, but if you look at the next case, it turns out that they're described by something called A2 and C2 cluster algebra. So they're defined by the mutation of this sort. And the number of cluster variables for A2 is 5, and then C2 and G2 are 6 and 8. And it turns out that you get exactly matching the symbol alphabet for these integrals. So that's quite remarkable. So already for the 2-loop and 3-loop 4-point integrals, you have the corresponding cluster algebra, so of two variables. Okay, so we want to do even more. So how about we go to more points? Well, it turns out that recently there's been important progress in mathematics. I should stop at what time? Yeah, I won't need as much. So I've been telling you about something called Grassmannian cluster algebras, but it's been there's been important work by mathematicians very recently. They presented an embedding of something called partial flag variety cluster algebras, F, and I will explain what it is, into the Grassmannian. So we would like to use these recent mathematical results to make progress for endpoint integrals. Okay, so I explained to you the initial quiver for Grassmannian cluster algebras. What is the flag cluster algebra? So flags are generalization of Grassmannians. So if you have k-planes and n dimensions, the flags are, flags d1, d2, n is d1 dimensional space, d2 dimensional space embedded in n dimensions. And there is just like for GRKN, there is this cluster algebra, this very well defined notion of a flag cluster algebra. So there is an object that exists in mathematics that is useful. Okay, so then again, I should maybe even skip this and just give you an example. For example, for a flag 2, 3, 5, that will be relevant for 5-point scattering. You could, so again, all you need to know is the initial quiver, and then you have your mutation rule, and you produce the variables. So this is a simplest example of a flag cluster algebra. There's a quiver, and these are the variables you get. And it turns out, so suppose we take it as a candidate for the object that describes, so for 4 points, we had only 2 coordinates. Here we have a lot more. So suppose we take it as an input. So it turns out, so we take this quiver and we produce the cluster variables. And then we compare that with this alphabet that's been, that I presented to you for 5-point scattering. So I told you for 2-loop 5 points, that's the alphabet. There are 31 letters. There are 25 plus some square root plus 5 non-planar letters. So then if you compare that data with the cluster variables for this cluster algebra, you see on the previous slide I had 31, here only 22. So it looks not enough, but if it turns out if you take all the permutations of this, you exactly reproduce this planar and non-planar letters that appear in two-loop 5-point scattering, and that's a result. That's our recent observation. So we want to again do more. And what about 6 points? So this is again very recent result of this 245 letters that were independently computed by two groups. Yeah, there, all of this. So it's a long list. However, if we take a candidate F2, 246, so that's the way the quiver looks like for this flat cluster algebra. Then we get the following observation. So there are 245 letters, and we get most of them except for the remaining 36. Okay, so there are exactly 135 cluster variables. There are square roots, which we don't expect to get. And then, so we were hoping we'll get it all, but unfortunately, 36 remains somewhat mysterious. So conjecture number one could be that maybe they drop out of the amplitude, because this is for the integrals. Now, what happens for the amplitude? We sum the integrals, so maybe some drop out. We were quite excited about this for a while until the computations came out, and Hen and Zhang and Cherin and others, out of 36, 24 actually appear. So they do appear. So you need some other description. So there's been work. So that's where we stand for applying flat cluster algebras to two-loop 6-point scattering. You can then go further, and I'm not writing it, but you can embed this into a larger object, and then several groups, Sonhi and also Sonhi here, and Papathanassiou in Greece, they were able to get them all. Okay, so that's the status. So far, I'm going to the outlook. So let me again summarize what I've said. So I presented to you various status and methods of both n equals to 4 Young-Mills amplitudes, and so you remember the 6 and 7 points have been computed to 8 and 4 loops, and then I showed you the symbol alphabet for 2-loop 5 points and 2-loop 6 points based on recent computations, and then I explained to you that they have deep mathematical structures. In particular, the symbol alphabet is described by cluster algebra. So let me just give some outlook to where this is going. So I was very narrow. I was focusing on this very niche observation, yet very important observation of just the fact that the alphabet is given in terms of cluster variables. So one can go further, and it's been work going further. There's been something called cluster adjacency. So when you mutate the quivers, some variables, so you do one mutation, and some variables appear next to each other, and these are called compatible. And it turns out that the variables appear next to each other in this symbol if they are compatible. Okay, if there exists a mutation, one mutation from one to another, those are, so this is something called cluster adjacency. And indeed, for flat cluster algebras, there's been also recent papers simultaneously with us by James Drummond and collaborators exploring this. Okay, so that's like a next order. So there's a symbol letters, and then the order in which those letters appear. Okay, but that's of course not all. You want a function. There's a systematic way to go from symbol to a function. And people have been doing this for the past 10 years in various ways, guessing of functions. But the interesting, important thing would be to have a mathematically rigorous way of doing it. So it turns out by mathematicians, so Rudenko mathematicians in Chicago, he defined a cluster polylogue function where, and classified those functions for various cluster algebras. So it would be good to make the connection between what mathematicians rigorously define to what physicists do, perhaps in somewhat ad hoc ways using mathematical guessing those functions. Okay, so cluster adjacency functions. What are the frontiers in high loops and high points? So a lot of Dixon bootstrap is based on the fact that symbol alphabet were just cluster coordinates. How do we know that's it? How do we know no new coordinates appear? Well, it would be nice to prove it, and there's been some attempts doing this, and probably the way to prove it is use Landau equations. And recently, nice package has been written by Misera and some students trying to use Landau equation to determine the symbol alphabet. So essentially, but unfortunately, anytime anybody wants to do something which is at the frontier of n equals 4, the package doesn't work or something. So it would be nice to have it really have a proof to in these high loops. And now it's important to also keep collecting more data. So far I told you these results for 2 loop 6 points, but there are also, for example, recent results on 3 loop 5 points. This is again for massless QCD, but for massless scattering, for massless integrals. It's very, very important so what I'm doing, I'm really just analyzing what other people compute and trying to make sense of this mathematically, but very, very important for this computations to be done. Now so that's high loops frontier. The high points is an important paper recently, which maybe underappreciated, is by Matthias Wilhelm, and Qi Zhang and Hans Spearing last summer, where, so these planar integrals for any n at 2 loops have been known from Nima's work over 10 years, but they've actually reduced this to one-fold integral. So it's important, there's in principle a lot of data and there's elliptics, there's a lot of more data available, so it's important to understand these integrals further. Okay, and finally amplituhedron. So some of you heard a lot, hopefully, maybe from Nima, a lot about amplituhedron in the past 10 years, but amplituhedron describes the integrand. However, recently, mathematicians, so Lauren Williams at Harvard and Matteo Parisi and many others, have been rigorously studying. Amplituhedron is some polytope, and you compute the volume of this polytope, and you get your integrand. And they've studied rigorously the tiling of this amplituhedron. And the tiles are cut out by collections of cluster variables. So there's a lot of important results, but all of that is so far tree level. Interestingly, there's been work, which I just heard in SwissMap 2 weeks ago by mathematician Pasha Galashin, trying to understand the tilings of loop amplituhedron at, trying to understand the tilings for loop level. So that may be study. There are also some interesting connections to origami and tilings and et cetera, but this is his tree-level paper, but there's also work for loops, and it would be very, very important because in principle we know the integrand and there's a cluster algebra there. How do you compare that with the result of the integral and the symbol letter? So there's a lot more to do, and it's great. There's a whole meeting on this amplituhedron in SwissMap 2 weeks ago in the Diablo, maybe 30 experts there. So there will be some progress there. Okay, and finally, maybe you've heard, insert your noun hedron. So amplituhedron has been there for over 10 years, and it describes n equals 4. Recently, over the course of 10 years, Nima says that the progress in this field happens every 5 years. So it started with amplituhedron 10 years ago. Then there was associahedron for trace phi cube theories. For colored scalar theories, there's been known something called associahedron, which describes the three-level scattering. There's a clusterhedron, which describes the one loop. And recently, there's been a lot of papers by Nima, his student Carolina Ficuerto, and others describing sophistohedron. So they were able to write down all amplitudes, any loop order, any dimension for trace phi cube theories. It's all, unfortunately, still colored. So all of these things that we learned for n equals 4 and what I talked about, now with the hope to apply to more realistic theories, have been recently developed for this theory, trace phi cube. So very interesting, would be very interesting to study the connection. So again, my focus was just n equals 4 and massless scattering, but there are these colored theories, and it would be interesting to explore. And cluster algebra plays an important role as surface cluster algebra in this surface dihedron story. All right, and now I will conclude. So I'll just to give you kind of a flavor of what I've been thinking about. So the evaluation of this two-loop amplitudes over a decade ago led to a lot of progress, including the introduction of symbol technology, which helps us evaluate integrals, to the discovery of the connection of cluster algebras. And indeed, some of these developments do satisfy the two pillars that I started with, because you could actually use these ideas to be able to compute something new, to being able to, for example, the hardcore 8-loop computation, to be able to bootstrap the n equals 4 amplitudes to a very high order. And now, again, to me, is very important that a lot of data is becoming available for just the massless scattering that I showed you, 2 loop 5 and 6 points, symbols are known. So there's a lot more to anticipate there. We hope there's a lot more to do.
Any question?
Very much for this very nice overview of the subject. Now, you emphasize very much the calculational part, so the use of these techniques for colliders, for post-Newtonian corrections, and so on. And of course, this is fantastic. But let me ask you, if you're looking towards the future with optimism, what would be the hope, the dream that you have in terms of understanding structure of quantum field theory? What could come out?
Well, I think, yeah, I mean, certainly what we've been seeing is the more calculations are done, the more structures we find. So eventually there will be maybe a final word. An object like amplitude for any standard model, which you compute its volume and you write down not just integral, but the final expression. Something of that sort. I think amplitude is great, but you need the final integral to write down. So an object without Feynman rules or anything just have all the structures, yeah, eventually. But again, this is just for pure amplitudes. There are other things that go, as you very well know, into the cross-section calculations that I'm not talking about. But this is just pure, quantum field theory objects.
Question? So if there is no more question, let's thank our speaker again. And next talk will begin after 50 minutes.